So as we are to consider our DC machines, this is a typical exam that we are going to work with. On question number 1, you were given 1.1, first part. A DC series motor is a variable speed motor, which is true. As we are to consider all those speed control calculations, that's what they're trying to say here. From where? Using a suitable formula, explain why the current drawn by this motor increases. Why is it that it increases when the motor is mechanically loaded? Remember the part of the armature. The armature current will increase due to what? The armature current is actually taken, remember, from your EMF equation of the motor. We saw this from our calculations, guys, that the armature current was taken from V minus E over the resistance of the armature circuit. Whatever that you're going to have in terms of the calculations, the E is to be taken or can be calculated. Remember, your E was going to be taken from your motor's constant speed and the flux. Remember, these two, they are proportional. We can see a relationship that is happening between the back EMF, which is the induced EMF, between the speed and the useful flux. The speed, when it decreases, this, because these two, they are proportional. E is actually proportional, speed and flux. So, meaning to say an increase in one increases another. If this speed increases, it means E is also increasing. A decrease in speed is a decrease also that is going to happen. As E is decreasing, is this value here is decreasing, what happens? Let's just say you've got values, guys. It's you're into mathematics, guys. Let's say you put this. V is not changing. It is maybe 200. Then your E, let us just say it is 100. And you've got a 0.5. I want you to see what was going to happen in your calculation so that you understand this explanation. Because there is just a direct thing, but there's no need actually for this. But let's just do it. This is 200 minus 100, which is going to be 100 over what? Over 0.5. You're going to get 200. Let's say, I'm just saying, let's say you're going to get 200 amperes. I want you to see what was going to happen. Let's say this value reduces here, E. Let's say it reduces. Okay? Let's say it reduces. We now have something like a 50 over 0.5. Let's see what's going to happen. It reduces, it's now a 50. So meaning to say we are going to have what? 200 minus a 50, which is what? 150. That will give us 300 amperes. That alone, I'm not going to have values that I'm going to work with more and more. But we need to see something here. E was 100. Now it is 50. What is it? It has reduced. Let's check the effect of armature current. It was 200 amperes. Now it is 300. It is increasing. So are we seeing what causes a decrease in this one? As it decreases, it affects an increase on this one. It affects an increase there in terms of what? Armature current. It will have an increase. Because that is what they want there. Increase the current of the motor, the armature current. So we saw what is going to cause that. These are the two guys that causes. E there must reduce. But what causes E to reduce, to decrease? It is the speed, because they are proportional. So the speed has to reduce. So this is what you can say. When the motor is loaded, okay? So when the motor is loaded, the speed, which is our speed N there, decreases. Remember the concept. It decreases. As it decreases, we saw the effect. Once this decreases, it affects what? It affects E. So thus, E reduces, which is our EMF. Thus, E also reduces or decreases. The reduce or the decrease that happened on E, how does it affect the armature current? And causing, in this case, the armature current to increase and causing the armature current to what? To increase. That is the condition there. The armature current we have to increase. So that's what they wanted you to know. They want you like, guys, do you know your motor? Do you know the operation of a motor? That's what they are into. Like, okay. 1.2, a 250 DC series motor runs at 1,000 revolutions per minute while drawing a current of 40 amperes from the supply. The resistance of the armature, the field, respectively, were given when a 0.2 ohm diverter resistor is connected in parallel with the field coils. The torque increases by, and the field coils are unsaturated. There, we are talking of a speed control, 1.21. Draw two fully labeled circuit diagrams to show the DC series motor before and after the diverter resistor is connected. Okay, we had a similar question like this one, just a little bit different. So this is what you're going to have, guys, 1.21. They need the two diagrams as we do understand our original, which is before, where we have got the original condition, and after, that is where we have got our final condition in that case. The final condition. So with this, we are given it's a series motor. On the initial part, it's a series motor. We're just gonna have our series presentation of a motor. Remember your series. Okay, the series field to the armature. Okay, just gonna need our series field here to the armature. That's our terminal voltage, which we are given in that case. It is what? A 250 DC. So that is 250 volt, runs at 1,000, meaning to say that's our initial speed, 1,000 revs per minute. And we are also given while drawing a current of 40 amperes from the supply. So from the supply, the load current is 40 amperes, which enters the field. It is the same field current into the field resistance, where we are given the resistances of the armature and the series field are 0.2 respectively. So the first one is of the armature, 0.25. That is of what? Of the armature, 0.25 ohms. So this is what you're going to have there. Your generated EMF 1 there. And as we do understand here, we're going to have the armature current flowing, and the resistance of the field we are also given on that respective concept, respectively. The other one is 0.1. This is what we have. On the final condition, what affected, it is a diverter resistor which was connected. And as we do understand, a diverter resistor is connected in parallel to the field. So as we are going to have our field, in this case, this is the field winding, a diverter is connected in parallel. That is what affected our diagram, is because of the diverter resistor, which was connected in parallel. So meaning to say the rest of this part is just going to remain as it is, your armature, this and that. Terminal voltage is not going to change, still at 250 volts. Armature, the load current, definitely this one is going to change. Like I explained from those classes that we had, I said the same load current here is this one that is entering these two. So it is going to branch another one into here, which is your ID in this RD or diverter resistor, which we are given its value. Remember, they gave us that 0.2 ohms into that. Here we've got your field. It's not going to change, 0.1 as it was given, but the current of the field, it comes out, all these. This one, it enters. This one, they're branching here to give us this. It is the same current that it was here entering. It branched. The sum of those two currents are now branching here to give us what? The armature current. So you can see that this armature current is simply the same as what? The load current that we had there. It is the one that entered, branched into this. Now it's coming out there. So that is the condition. Having your generated EMF2 there. This is it, guys. It's your motor, remember? And you're going to have the resistance of the armature, 0.25 ohms as we had before. So remember your diagrams, guys. They just want you to have the basics there. And they are saying the torque is increased by 20% and the coils are unsaturated. So if the torque is being increased by 20%, what is the effect? T2 is equal, an increase, I said you have to add to 100%. When it is originally there, it is at 100%. So it increased by 20%, you must add 20%. So it's going to be 120% of what? Of T1. Divide this one by 100. So it's going to be 1,2 of T1 at the end. So this is the torque relationship. So meaning to say that torque equation also has to play a role. All right, no problem. Let's answer our questions, guys. Let's answer our questions after that. 1.22. Calculate the speed at which the motor will run after the diverter resistor is connected. After you connect this diverter resistor, the speed is going to change into N2. So they want you to calculate that speed, N2. All right, we do not know that. That's our 1.22. Let's see. Remembering that as we are to consider our speed calculations, always the main speed formula has to play a role. What is your main speed formula? E1 over E2 is equal to N1. Are we going to use the flux? We are not given. We use the flux when you're given. Remember, you can use that N1 flux 1 over N2 flux 2. We use this when you're given. When you're not given, flux approximates to what? The field. So you're going to use the field current there. Field current 1, N2, field current 2. This is where you are. What is it that you need? You need to calculate the speed. Final. Are we having this? No. Are we having this? No. Are we having this? Yes. Are we having this? No. Are we having this? No. These are to be determined, calculated. Let's see. On a series condition, it is easier because those currents are the same. So let's work on the series first, on the original condition. From that original condition, what is it that we can have? Load current is the same. It's a series. So it follows that the load current is the same as the field current. It is the same as the armature current. Why am I having a 2 while it's the same at the first second, guys? This is 1 there. armature current 1 is also the same as what we had there on the load, which is what? 40 amperes. So the field current is there. So we have this. Okay. Let's see. We can also calculate E1. We also need E1. As we can see there, we need E1. We are still on the original condition. So let's calculate E1 from there. The generated or back EMF, V minus armature current 1, resistance of the armature circuit. What is it that is there in the armature circuit where the armature current is flowing? There is RA, there is RF in series. So it is the sum of RA and what? RF. Remember your series consideration. So E1 was going to be calculated. Your V, 250 minus armature current 1. Remember, it's the same there. Armature current 1 is also what? 40. So that was going to be 40 into these resistances that we have added together. RA 0.25, then RF 0.1, the resistance of the armature circuit. Make sure that you also watch the part 1 where I talked about these resistances of the armature circuits as we consider different circuits. Each and every circuit, you must know how to obtain the resistance of the armature circuit. So it was going to give you 236 volts. That's your E1, which we need here on our formula. Remember? So E1 is there. What is missing? IF2 and E2. Where can we have this? Let's consider our final and see what can we obtain from there. So from the final condition here, let's see what is it that we can have, because we have a lot of things that we need to consider as well from the final condition. If let's say I wanted to calculate IF2 because it's the one that I'm seeing here that it is needed, IF2, it is needed. I was going to use the current divider rule. Remember I talked about that? The first part of this I explained, opposite resistor on top. So you're going to have IF2 equal to what? Opposite resistor on top, RD over what? The sum RD plus RF times the current which is being supplied as your load current, which is that one, the load current 2. You're supposed to use that as load current 2. But are we having that? No. So guys will see that 1, these values they're there. This one is there. This one is there. This one is there. But you are now short with this one. There is no condition that we are given that the load current here is going to remain the same, where we can take it from here. No, this one, it's not like that. So what can we do? We know that these two, they are the same. Like I was explaining, armature current and the load current from that idea, they are the same. These two, they are the same. So in place of this load current, I can also use the armature current instead. But do I have that armature current too, so that I can obtain this? I do not have this one. I do not have that. Where can it be obtained from that? This armature current too, from the torque, as we had before, from the torque. Remember we had that in our calculations in our first class. I said armature current too, think of what? The relationship of the torque, because it carries that. So you are going to think about calculating that. Let's see if it is possible here from the torque. All right, from the torque equation that we had before in our classes. Remember I said from the torque you're going to have T1 over T2. All those calculations, guys, T1 over T2 is equal to IF1. Considering the armature current, this will be armature current 1, IF2, armature current 2. It can be given in terms of the flux. Remember, this is same as the flux. So you cannot use something that has got the flux there, because we do not have the part of the flux. So this we're not going to consider. We're just going to consider the part of the field. The relationship there is the T1 and T2. So T1 cannot be replaced because that is the original condition. So you just write it as T1. It is T2, which you take in terms of what? T1. That's 1, 2, T1 is equal to what? The field current one, we said it is there. Remember, it's a series. So we just said it's the same here. If we still remember, field current is same as the load current one, which is what? Which is 40. All right. You are on the first. We're talking about field current one, not 2. So this one is there. It is a 40. Same as the armature current. Remember, it was the same value, a 40 again, over what? Field current 2. You are going to see that you will be stuck because you do not have a field current 2. You need 2 things there. You're going to cancel this. You see, okay, T1 and T1, they're canceling. This is going to be 1 over this. But there are now 2 unknown values there. IF2 and IF. So you see that, okay, guys, I have to find what? One of these. Can I have, is there a part where IF2 that it can be written in terms of this? So if you check the previous introduction, I talked about that, where you have to consider this equation now, or the one that we wrote here, the one that I left here. Because you can see that armature current 2 is needed here. It is needed here. So what are you going to do? You are going to write IF2 in terms of what? Armature current. So you are going to express the field current in terms of what? In terms of the armature current. In terms of the armature current. Remember, these 2 are the same, so we're not going to use the load current. We'll use armature current there instead. So the formula now can give us what? RD, we just have to substitute. We have this RD. What is your RD? Here, RD 0,2. So that's 0,2 over the sum, 0,2 and what? 0,1 for RF. So you're going to have 0,2 plus 0,1 times the armature current 2. So in terms of I2, or in terms of this armature current, we are going to have this IF2 written as 0, if you divide this on your calculator, it was going to be 0,6666 and so on and so on, which is 0,667 to 3 decimal places of what? Of the armature current. It's an equation, this one that we have, which still we have what? 2 unknown values. Let's just leave it like that. Because IF2 has been written in terms of what? In terms of the armature current. So it gives us the power even to remove it here where it is on this equation where we left and write it in terms of the armature. Remember, this is the missing part. We cancel this T1 and the missing part was on this one. So we have it in terms of the armature current. So we can substitute now and say that is going to be in place of that armature, in the place of this, I'm going to substitute now equation 1, equivalent of that one. So you can write another step, but as for me, I can just remove that. Write it, the answer there in place of that IF2. What is the answer? 0,667 of what? Armature current 2. You write the equivalent there. It was 0,667 of what? Armature current 2. This is something that we calculated in place of this. So you see, if you know these stages, therefore you don't need even to write this, then you leave it. You go, no, you just have to calculate, you know, your stages. Okay, if it is like this, I'm going to calculate my what? My field in terms of the armature. Then I have to go to the torque now, where I find the armature current 2, where I have the field in terms of the armature current. So this can be calculated. Remember, we cancel this T1 and T1. So cross multiply, guys. What are we going to have? 1 times this. It is going to give us 0,667 armature current and armature current multiplied together. We are going to have a squared, which is equal to 40 and 40. They multiply each other. So it is same as we've got, just like what we multiplied. So it's same as we've got 40 squared. Or you can just write 40 times 40. There's no effect. Times what? Times 1,2. Everything over what? 0,667 over 0.667. So dividing by this, you're going to have armature current squared, not armature current. So to obtain the armature current, what do? Introduce the square root covering up everything there. You are going to obtain the armature current now. So you see, guys, how you play around with these techniques. One is missing, one is, you do like that. So the armature current was going to be 53.652 amperes. Why do we need this armature current? We need this in order for us to obtain E2, the one that is missing here, E2, inside of E2. Armature current is there. Okay? Also, we need this armature current in order for us to have this field current too again. These two, they depend on that armature current. How? How so? All right. This is our armature current. Remember from equation 1, this one. We wrote IF in terms of what? In terms of armature current. So it can be calculated now. It depends on that. So you see where that plays a role. So from the armature current, two things are going to be calculated from there. The field current from the relationship 0.667 times what? Armature current, the one that we calculated. Remember, we got 53.652 amperes. So that field current was going to be calculated 35.786 amps. So we have got field current, the numerical value that we need on our formula here. What is left? The generated EMF E2. So E2 can also be calculated from our circuit here on the final condition. Let me, since we now have this, guys, let me just remove this part so that we do not end up having those removals. Now take out everything. These softwares, you know them, guys. So like I said, we need E2. Now, let's calculate E2. From the final condition, E2 can be determined, just like how you calculated E1. V minus what? Armature current to resistance of the armature circuit. So V, this, we calculated this, remember? The resistance of the armature circuit. What type of a circuit are you having there? Where the armature current is flowing, it is affecting these two in parallel and RA. So meaning to say, it is going to be product over sum and that RA considered. Okay, remember I talked about this like I was saying, guys, on the introduction. So I said when it is like this, your RAC is going to be equal to RA added to the parallel combination of these two, RD and RF. Remember your parallel product over sum. Product over the sum. Just like that. So what is your RA? 0.25 plus the product of RD, 0.2 times RF, which is 0.1 over the sum, 0.2 plus 0.1. So in this case, the resistance of the armature was going to be determined, or it was going to be calculated. And that was going to give us 0.317 ohms, resistance of the armature circuit 2 of the final condition. And with that, E2 can now be obtained, this part of our E2. Because we are saying it is from this formula and we have it now, the resistance of the armature. So V, the terminal voltage, 250. Armature current 2. We calculated this, if you still remember, when we calculated this armature current 2, it was 53. This one, it was 53.652. Remember that value, guys. 53.652. The resistance of the armature circuit, 0.317. That resistance of the armature circuit. So this was going to give us the value of E2. And that was going to be 232.992 volts. Just like that. Where are we going to use it? Remember, your main speed formula, you must find everything. So this is now the N2 now can be calculated by substituting everything that we had. E1, we calculated this, 236 over E2. This is the value that we just calculated now. Remember, E2 we just got 232,992 is equal to N1. We are given 1,000. The field, remember the part of the field, this is one that we said in series, the load is the same as the field, so it's the 40 amps there. Remember here, 40 amps. You substitute everything. N2 is the one that you need. The field on the final condition, if I did not remove this, I just stop. All right, but if you still remember, guys, we calculated that. It's only that I removed those values because there are so many values that we have there. But if you still remember, this field is the one that we calculated and it gave us 35.786, the one that we calculated from the relationship of the armature and IF2 as an equation from your equation 1. Remember that. So N2 cannot be calculated. This is what you need. From your question, this is what you need. So find that N2. So just like that, guys. So you're going to cross multiply this and that, all right? So let's add up, let's cross multiply this to this is gonna be N2 times 3. All right, in actual sense, guys, this is how you can simply do, you can simply take it this way. For there, we're gonna have a lot of things. Oh, let me just multiply 35.786 times 236 so that all of us, we can just understand each other here. This one multiplies this side, so it's gonna be already, there's a 1,000 there, times a 40, the 232 also multiplies there, 232. Right, very sorry for this here. So it's going to be 232.992. We need this speed, so definitely going to divide by all these. 35,786 times 232. Also do the same thing, 35.786 times 236. So definitely this was going to cancel. You have your N2 speed, the one that you are being asked there, right? The one that you are being asked. Okay? The one that you are being asked. So therefore, our speed is equal to what? It is equal to this. Simplify everything there. You are going to obtain 1,103, it's going to be 5089. This and that. So we're going to change this into 509 revs per minute. This is the speed in revolutions per minute. So your speed control is in your hands now. We talked about these guys. Where there's a question, the comment section is there. Let me know so that we can work on that area or on that question paper. Maybe there's a question paper that you try to attempt on your speed control, then it is something else, or your DC machines. And there's something else, let me know so that we can try by all means to work on that as we are revising for the exams that are ahead of time. Let us add as much question papers from the idea that we just have. Add as much question papers as you can. So this is it, guys, from MathZone African Motives. Till we meet again.